Now let's learn about CNNs, Convolutional Neural Network. So convolutional neural network is different from artificial neural network in many ways. Primarily, convolutional neural networks have convolution instead of dense connection. In the previous slide, we have seen that in artificial neural network, each neuron is connected to every other neuron in the previous layer. This is called dense connection. Benefit is each neuron can see the entire input at every level. It can see the entire input of from the previous layer, but disadvantage is it's so difficult to learn all these weights. In each neuron, the weights have to be learned independently. This neuron have, let's say, 3 weights, then this neuron also have separate 3 weights or 4 weights. 4 weights here, 4 weights here, 4 weights here. These weights are independent. Each neuron have to learn a corresponding weight separately, and often this entire input may not be required. Example, let's say a person is standing here, his head, if this neuron is looking at the head, there is no need of getting that leg pixels in this neuron. So if this neuron was looking at head portion alone or close to that, then this could have focused on learning more about head. So that's where CNN comes into picture. In convolutional neural network, main difference is convolution, which is having weight sharing. So as you can see in this diagram, let's say this is the input image. This is what we are calling weight, and this kernel. This kernel is multiplied by with every patch of image, not the entire image. A patch of image, let's say 3 by 3, and then we will use the same weights and multiplication and addition. So basically convolution dot product. In the next patch we will take, like basically we can shift this window and do dot product, and basically sum of dot product, which will dot product itself is sum dot multiply and add with these weights, and that value will be assigned at each location. So for this image, when we do convolution with this kernel of matrix, we will get another image, 2D image itself, and the number of pixels will be based on how much we are shifting, how many windows we are taking. So basically how much is stride, we call it stride. Basically if you are moving 1 pixel, first we are taking this window, and then if you are moving towards right by 1 pixel, then we will call stride 1, and if you are moving by 2 pixels, we will call stride 2. So first this window, and stride 2 means the next here this window, like that. So that is to x direction, and then once you have reached the end, then we can move down by 1 pixel, means stride 1 along y-axis, and then again we can traverse the entire x, come down. So if you are moving down by 2 pixels, then we can say along y-axis stride 2. Typically it is just a stride 1, and same in x-axis and y-axis. Typically that is used. Also, if you want to retain this like same number of, like let's say this is 10 by 10, and you want the output also to be 10 by 10, then you need to pad the image. So that is where padding comes into picture. In like if in this case we have to give padding of 1 pixel, then here one row will come and here one column will come, and then for this pixel we will have one window here, and that window we will multiply and add with these weights and put the value here. The advantage is with that padding we will get the same number of pixels as the input image size. That size reduction will not happen. So yeah, so that is basically convolution. Most important thing to notice here is we are using the same metrics, same kernel to do multiplication addition in every patch. So thing is, let's say this is a, as you can see example for here you can see 5 -1 -1 -1 and here 0. So this is a filter or maybe an edge filter. Let's say 2 2 2 0 0 0 -2 -2 -2. So that means it can detect whenever there is a vertical line, this filter will be that output value will be more. And similarly, we can have a horizontal filter as well, like 2 2 2 0 0 0 -2 -2 -2. That can act as a horizontal filter. So the what will happen is we will just start with random values for this weight, and this will learn by itself whether to do a horizontal filtering or vertical filtering or whatever filtering this is supposed to do. That will learn by training. We will give input, we will give output, and for every, like, again back propagation only, and with back propagation these weights will be adjusted. And oftentimes this input, in the input layers, it will look like they are doing either vertical line detection or horizontal line detection or diagonal line detection. Basically that they act as corner detection filters or edge detection filters, sorry. So the like often input layers will be edge detectors in order to detect this any kind of lines or change in shade, any kind of let's say patterns. If there are some small patterns in it, this initial layers will learn to detect those patterns, small patterns. And then going forward, like this same convoluted output will be again given to another convolution layer. It will again do same thing on this resulting image. So it will be able to learn even deeper concepts, like here this it extracted these edges. Then based on that edge, next convolution layer can learn about like structure connecting those edges, and then next can even learn structure connecting those edges. Like that, eventually it like once we reach the towards the end, it can see the entire input. So we'll come to that. So other than this convolution operation, we have max pool. That is another thing introduced in the CNNs. So max pool basically, as we can see here, so let's say we have done convolution and we got this image, output image. That output image often have, let's say, if there is a edge here, this next window also might have an edge. Like here we got an edge, then most likely here also there will be an edge. And oftentimes this information might be redundant, and that is one thing. Or there is like edge is what we are looking for, and here there is no edge. So that is not of interest. Like wherever we got an edge, that is what we want to retain. In that case, we can go for max pooling, or basically it will reduce the dimension, image dimension. It will downsample the image, so that way we will retain the important feature. At the same time, we can reduce the size. So if we keep on, we have seen that earlier, like we had to do so many convolutions to get this image, and again, if you are doing same number of convolution, like that, we need to reduce the number of convolutions. So for that, we will take a max pool of these values, and we will retain the largest values in each pixel, and that way this 1, 2, 3, 4, 4 by 4 matrix will become a 2 by 2 matrix. So here this large image will become half the size of it, and after max pooling, and then next max pooling again happens in the layer. Sorry, again next convolution we will do. After that convolution, we will do max pooling once more, and that time we will reduce the dimensionality again by half. So every time we do a max pool, we will do keep on reducing the size by 2. So it's not mandatory we have to do 2 by 2 max pooling. It's optional. But typically, we do like this. So that is max pooling. So and the benefit of this max pooling is shift, rotation, scale, invariance, bringing in this invariance, because this even the if the edge is shifted towards left or right, the result of max pool will not vary. So that brings in a level of invariance. Actually, this invariance is also there because of this convolution. Whatever feature is there, if that feature entirely shifted towards right, then this weights anyway is shared, so that features will be detected little towards right. It will be captured here. So basically, because of convolution, we are getting certain invariance. Not all the invariance, some invariance we are getting. Okay, so that is another important layer came in with the convolutional neural network. Then our simple nonlinearity. So earlier in the ANN, it was sigmoid primarily because it's a really good nonlinearity. But in CNNs, this ReLU was introduced. ReLU is nothing but just a max of 0, comma, whatever is the input value, just a straight along x, if you draw x-axis, y-axis, 0, and then whatever is the input, like x equal to y equal to x, like that, a graph. So here the benefit is, if the x is less than 0, y is 0. If x is more than 0, y will be equal to x. And this introduces, or this brings in two things. First is, since y equal to x in this positive region, there when we calculate gradient, one is this gradient is constant. Sorry, gradient is same at whatever level of x. So that way there is less chance for vanishing gradient whenever the x is in the right, when x is positive. And another thing is sparsity. So if when x is less than, or input to this nonlinearity layer is less than 0, it will be forced to 0. Basically, max of 0, comma a. So less than 0 means it will be forced to 0. It will be put into 0. Means that input is killed. So that way sparsity is coming. So in the previous fully connected or artificial neural network, every neuron was connected to every other neuron, and in the like adjacent layers, and there was no sparsity. So here this sparsity is coming. So here and there it will become like input to the neuron becomes like output of the neuron becomes 0. So the next layer doesn't have to worry about whatever is 0, and this helps in better training and more stability. So next is batch normalization, yet another feature. This helps in faster and more stable training through normalization of the layers inputs by recentering and rescaling. So basically, we can simply say mean, standard deviation, bringing into a common scale. Like basically, recentering means that mean value will be brought to 0 or whatever value we need, or basically that mean value is also learned, not 0, sorry. So basically centering the value as well as scaling the value. The range, if it is from 50 to -50, it will be scaled to -1 to 1, say, or basically that also again learned. So that is recentering and rescaling. Learned recentering and rescaling is what is happening in this batch normalization. So that also helps in faster and more stable training. So these are all the advantages, and many layers got added into convolutional neural network, and that's how it became more stable, or many varieties of CNNs evolved later. But in crux, this is it: convolution max pooling, batch ReLU, and batch normalization. You repeat that, and you will get really deep networks. And thanks to this ReLU and all these other improvements, they learn. And again, with weight sharing, so this thing can learn from less data, and the network will be more stable. And this is like night and day difference with this earlier artificial neural network, which was so difficult to train, and it become deep, then becomes almost unusable, like almost impossible to train. And another important feature you need to notice here is this feature extraction. This acts as a feature extractor basically. So CNN, we can say, is a feature extractor, and finally for classification, we will normally add a fully connected network towards the end, because all the features are extracted. Based on these features, some final calculations, which considering the entire input. So towards this end, the entire input is squashed to few values, and those, based on those few values, we can, or basically that we can give to a fully connected network, and finally it can do a decision making. So we can't say decision making happens here; it happens throughout. Just that once it reaches very low dimensionality, then can be given to. Then onwards we don't need convolution. We can instead give it to fully connected network. So yeah, that is a brief on convolution network.